think it's probably the one that has the most applications, especially in different fields. We'll do kind of like the basic version, like just get us through the calculus version. But in math, really, whenever we talk about optimizing something, you guys are trying to find like the optimal situation, so either like the maximum or the minimum of something. These problems are basically going to be the applications of absolute extrema. There's other ways to do these problems, so often we can solve problems multiple ways in mathematics. But these problems do show up a lot in like economics and engineering, where often we want to find like the maximum cost or like the most efficient of something, and things like that. We just need to kind of focus on the calculus aspect of it. So whenever we do an optimization problem, we're going to be maximizing some quantity or minimizing some quantity. Some guidelines I use when I'm doing these problems, I sent this out to you so you don't have to write it all down. But basically, when you're doing an optimization problem, you're going to write two equations. You're going to have one that I call the primary equation and then one that I call the secondary equation. The primary equation is the one that you're optimizing. So it's going to be the one that you want to maximize or the one that you want to minimize. And then not always, but most of the time, there's going to be some sort of secondary equation that will just relate some other variables together. And we need that secondary equation because in the optimization problem, like we're not taking the derivative with respect to time. We just want to take the derivative basically with respect to the independent variable. So there's no implicit differentiation. So we want all the variables on one side of the equal sign to be the same. So we don't want to like mix variables in the equal sign. And where like the calculus knowledge comes into play is like we know in calculus a minimum or maximum, or I should say a potential minimum or maximum occurs at the critical point on the graph. And we know that the critical points occur when the derivative is equal to 0 or when the derivative is undefined. So the main idea with these problems is we'll have some equation that we want to minimize or maximize, and we'll take its derivative and then find its critical point. So for example, a classic kind of optimization problem. In fact, I know if you had Miss Porter for a math class, probably I guess 2 years ago, in the polynomial unit, I know she makes you a problem where you have like a sheet of paper and you're folding it to make like a box, and you want to find like the maximum volume of the box, and you solved it without calculus. We'll be doing kind of the same thing today, but with calculus. So basically, it's going to be talking about how we can maximize or minimize certain things. So like in that example I was going off of, if I wanted to maximize volume, my primary equation would be volume. So that's what I will take the derivative of, and I'll basically find the critical points of the volume equation and then go from there. Oftentimes we're lucky and we'll only have one critical point. If you get one critical point, that is the maximum or minimum. If you do end up with more than one critical point, you do need to make a candidates test. I should put a little kind of disclaimer there. Sometimes you can rule out critical points, like if you're maximizing area and a certain critical point gives you an area of 0, like clearly that's not going to be the maximum area that you can do. So for the example, I'm just going to look at 4 examples today. I try to just do 4 different types of examples. So I have one that's just based off of like numbers. I have one that is more geometric, or really 2 that are geometric, and then one that's more of like an actual kind of like physical example that we can think about. So for our first example is going to be this problem. So it says find 2 positive numbers whose sum is 17, so that the product of the larger and 6 more than the smaller is maximized. So yes, I will say, disclaimer, many of these optimization problems, if you're good with like logic and good with problem solving, you can probably solve these without calculus. Oftentimes they're written so they're a little bit harder to solve without calculus, like it just says 2 positive numbers. They don't have to be whole numbers, they can be fractions, which of course increases the possibilities that you have. And oftentimes the AP exam will ask questions in a way asking for you like the setup or just like where the critical points, just so you can force you to do the actual calculus. So this is where kind of your just like general math skills come into play. You need to be able to write an equation based off of the situation that you see. So I see that we have 2 positive numbers whose sum is 17. We don't know certain things in math, so we can assign variables to them. So I'm just going to let the variables x and y be my numbers. Again, you could use A and B, it doesn't matter. We just need some variables to represent something. And then we want to write the equations of the situation that we see. So first off, we know that our primary equation is going to be what you are maximizing or minimizing. In this problem, what are we trying to maximize or minimize? The product. So we basically, the one that we will eventually take the derivative of is going to be some equation representing a product. So I'm just going to use P for product. It says that the product of the larger, I'll just let X be the larger one, and 6 more than the smaller one is maximized. Again, different equations you can write, but that is what I get from that statement. We want the product to be maximized, so I need to be able to write an equation fitting that situation. The issue with this equation written as it is right now, when we do an optimization problem, we're taking the derivative with respect to the independent variable. And right now we have like a P, an X, and a Y. We want to reduce the number of variables in the problem. And that's where the secondary equation is going to come into play. The secondary equation is going to be one that is like a static equation. So it's not the one that you're trying to minimize or maximize. So in this case, our secondary equation can come from that first statement. We have two positive numbers whose sum is 17. So I know that X plus Y is equal to 17 always. And so then the idea behind these problems is we want to use that secondary equation to simplify the primary one. So basically you're going to do some substitutions. Then when you have a nicer primary equation, take its derivative, find the critical points, and then use that to answer the question. Choices you can make, there's often lots of different routes to solve these problems. Like in that secondary equation, I can solve for X or I can solve for Y. It wouldn't matter which one you solve for. We just need to write that primary equation to only have one set of variables on that left-hand side. I'm going to go ahead and solve it for Y. I just like taking my derivative in terms of X just because that's what we're used to. So I can see that Y is equal to 17 minus X. And so what I can do is now I can plug in Y is equal to. I could have easily solved for X and plugged in what X was equal to. But my new primary equation is this product is equal to X times my Y value, which was 17 minus X, and then plus 6. And since we're minimizing or maximizing the product, that's what we're taking the derivative of. I would, of course, simplify that equation so it's a little bit easier to find the derivative. So we have the product is equal to X times 23 minus X. And again, I don't really want to do the product rule, so I can just go ahead and distribute that X across. This equation right here is kind of like my simplified primary equation. That is basically the one that we want to minimize or maximize. So if this was not a calculus class, you would, that's a quadratic equation. Like you know how to find the vertex of a quadratic, so that negative b over 2a. Or maybe use your graphing calculator to find the minimum or the maximum. But this is calculus, so we can rely on our knowledge that possible minimums or maximums occur at critical points. So I'm going to go ahead and take the derivative of the product. So that's going to become 23 minus 2x. And then critical points occur when the derivative is equal to 0 or when the derivative is undefined. This is just a polynomial, so I know that the derivative is never undefined. But I can go ahead and solve for x, subtract the 23, divide by negative 2, and x is 23 halves. That is one of my positive numbers that fits the scenario that we have. So if I want to find the other number, we can just go back and plug it into our secondary equation. So I wanted to find y, and I know y is 17 minus 23 over 2. You can leave it like that. I'm going to simplify it just so it's easier to talk about. 17 minus 23 over 2 is 5.5, and we get 11 halves. So looking at what we found, just to kind of put it in perspective, so like we're just looking for two numbers that would add together to give you 17. 23 over 2 plus 11 over 2, that's going to give us what we're looking for. But we have found the two numbers that add to give us 17, but also have a maximum product. And that mainly just gives us the idea of how these optimization problems work. We're going to have some equations. We're going to figure out the one that we want to optimize, and we want to be able to write it in terms of one variable, take its derivative, and then find the critical points. Questions or concerns about that one? All right, let's look at this one. That's more of a calculus problem. I actually got this one. This one is based off of an actual free response question from an AP exam. I mean, it was part B of like a 4-part one, but it was a part of a free response question. And I have what point on the graph of y is equal to x squared is closest to the point 3 comma 1/2. So just to kind of get an idea of what we're looking at, so we have this graph. There's y is equal to x squared. I have the point 3/2 comma 1/2, or 3 comma 1/2 that we got. And we want to find the point on this graph to where that is ending up being the closest to the point 3 comma 1/2. This is an optimization problem because we really are minimizing or maximizing something. If it's saying the closest, we are basically minimizing something. Minimize, if I can spell. What are we basically trying to minimize in this case? The distance. So what formula do you think we can use for our primary equation? The distance formula. So basically we want to figure out how this distance can be a minimum. Like it could be any point along the graph. Like visually I know it's going to be somewhere located there. So my primary equation is going to be the distance formula, which we know. Here is the distance formula. But again, I really want to kind of rewrite it to be in terms of this problem. So looking at it, what are we trying to find? We are trying to find the x comma y that is closest to the point 3 comma 1/2. So there's the 2 points that I can go ahead and plug into my distance formula. So I can see that the distance is equal to, I have the change in x. Order doesn't really matter, but I'm going to do the variable one first. Plus the change in y squared. And then since that is what we are trying to minimize, we want to find the closest point, we do need to take the derivative basically of the distance formula. Before we can take the derivative, what's the issue with how we have it written so right now? Besides that, it just looks like it's going to be a gross derivative.
There's 3 terms.
Like we need to get rid of one of those, so we need, that's the primary equation. What do you think the secondary equation is going to be? Y equals x squared. They gave it to us. So basically I can take this problem. You could solve it and say x is equal to the square root of y, but that's kind of gross. I would just leave it, well, y is equal to x squared. So my simplified primary equation will look something like this. So I have x minus 3 squared plus what is y? Y is x squared. And so we have this new kind of simplified primary equation. One mistake I often see people do with optimization problems is like they work so hard to get the primary equation, and that's what they set equal to 0. But remember, this is calculus. We need to find the critical points. That's where the min or the maximum is going to be. So we do need to find the derivative of this. Don't overcomplicate this. Like the distance formula, if you're taking the derivative of it, you're just going to have to do like the chain rule several times. No big deal. We can do that. So if I'm taking the derivative of this, so this is going to be d prime. This is the square root of a bunch of stuff. So I can go ahead and do the chain rule. The 1/2 is going to come down in front. The inside is going to stay the same, and the new exponent is negative 1/2. So again, the inside is the same. And then chain rule times the derivative of the inside. And we'll have to do a little bit more chain rules as well. So the derivative of x minus 3 squared, 2 comes down in front, and I have x minus 3 to the first power, plus that second piece, that squared comes down in front, x squared minus 1/2, the new exponent to the first power. Don't forget the chain rule. And so that is my derivative, which looks scary because what do we need to do now with that derivative? set it equal to 0, and remember critical points, also find where it is undefined. But it actually works out pretty nicely, so I'm going to clean it up a bit because that's a lot going on right there. So if I clean it up, give me a little bit more space. I have d prime is equal to, so 1/2, I have a 2 in the denominator. That first part of the tuning rule, all that's raised to the negative 1/2, so I know it's going to end up being in the denominator. So I have this x minus 3 squared plus x squared plus 1/2 squared. And then in my numerator is this piece, which I am going to go ahead and kind of simplify before I put it down. So I have 2x minus 6. This is a 4x times an x squared minus 1/2. Distributing that across, I have 4x cubed. 4x times a negative 1/2 is minus 2x. The 2x's cancel conveniently, and we end up with 4x cubed minus 6 in the numerator. Could factor out a 2 and cancel it as well. But that's what I get for my simplified derivative. Yes, Matthew?
Should it be x squared minus 1?
Oh, in the denominator, yes. And so from here, now we just need to solve it. Like, that's the hard part, simplifying it. But we know we need to find the critical points. The critical points occur when the derivative is equal to 0 and when the derivative is undefined. The derivative is equal to 0 when you set the numerator equal to 0. So if I have 4x cubed minus 6 equal to 0, x cubed will be equal to 6 over 4. So x will be equal to 6 over 4 is 3/2. And then take the cube root of both sides. Remember, an odd root does not have plus or minus. We also technically need to find where this derivative is undefined, but we're not going to overcomplicate it. Because if I look at setting this denominator equal to 0, looking at that denominator, this square root portion is exactly what we saw in the distance formula. So can this square root ever be equal to 0? No, you can kind of look at it. Even if x itself was 0, like something squared plus something else squared, in this problem, that distance is never going to be 0. So this denominator is also never 0. So this derivative is technically never undefined. So thankfully, we did all the algebra. We just have one critical point. So let's go back and answer the question. What point is closest? Well, the point that's going to be closest is the one that has an x coordinate. That's the cube root of 3/2. And to find the y coordinate that goes along with it, well, I know that y is equal to x squared. That's the function. Well, if I have the cube root of 3/2 squared, that's the same thing as saying 3/2 raised to the 2/3 power. So this is the coordinate on the graph of y equals x squared that ends up being closest to the point 3, 1/2. Questions, concerns about that one? Again, I just want to emphasize like the process again. Like I think the hardest part on this one is just like finding the derivative and simplifying. You have your primary equation. That's the thing you're maximizing or minimizing. You need to write it in terms of a single variable. And then you want to find the critical points of that primary equation, which involves taking the derivative and then finding where that derivative is equal to 0 and possibly undefined. If you only get one critical point, that is your minimum or maximum. So this one would just have a minimum. That distance will be when x is the cube root of 3/2. Try that third one on your own. To get you started on it, so we have a circle. X squared plus y squared is equal to 25. And you're looking at the top half of that circle. And inside that top half of the circle, inscribed is a rectangle that's being drawn out by that point P. So like that's just one possible rectangle you could draw. For example, I'll do a light color. If P was up here, the rectangle would look something like this, or maybe if P was here, like the rectangle could look like this. But basically, you want to find that coordinate of P that would draw the rectangle with the largest area possible that fits inside of the circle defined. So as you're trying this on your own, again, the idea that you're thinking about is you need to figure out the primary equation. The primary equation is what you're minimizing or maximizing. It says you're maximizing the rectangle's area, so you need to find some sort of formula for area. And you need to write that area in terms of one variable. These problems I think are nice because if you're looking for the secondary equation, they give it to you. That is the circle equation they give you. But go ahead and see what you can do with this one. This one is a little bit more complicated because you will get more than one critical point, but there will only be one of them that really makes sense in the problem. So maybe I should start off and see if you can write a primary equation in one variable.
Mr. Brown,
Yes.
for so I got plus or minus,
You're in the
square-
top half of the circle, so you don't need plus or minus.
Oh, just the, okay,
Yeah, just the plus.
thank you.
Looks like most of us have got at least the basic primary equation down. So if I'm writing the area of this rectangle, I know that it's being drawn out by this point P that has coordinates x comma y. So we know that x is basically how far we're going out this direction. So what can be an expression you use for the base of that rectangle? 2x. So like if you go out by x, that's really just half the rectangle. So the base would be 2x. And then the height of that rectangle is technically which variable? Y. So it's basically the y coordinate that we see. Looking at the area being equal to 2xy, that's an issue because we have too many variables. We just want it in terms of one variable. Doesn't matter which variable you solve for. When I have x's and y, I just like dealing with x's, so I would probably solve this for y in terms of x. And again, you wouldn't have to worry about the plus or minus when you take the square root because you are looking at just the top half of that circle. So y would be equal to the square root of 25 minus x squared. So my primary equation that works a little bit better is 2x times the square root of 25 minus x squared. So that's my primary equation. We want to find the maximum possible area. So we want to find the derivative of that. Make sure you find the derivative correctly. There's a product there with the chain rule. So I have a prime. So I have the first times the derivative of the second. Don't forget your chain rule. Plus the derivative of the first times the second. You want to find the critical point with that area derivative. Right now, that's a pretty gross equation to solve. Two ways you can simplify it. You can either rewrite it and get a common denominator and add things together, or you can do like some fancy factoring and simplify it. I think on the last example we did, I kind of did like a common denominator. So today I'm going to show you how to do the fancy factoring, but again, you will get the same answer. Before I do the fancy factoring, I'm going to go ahead and cancel out at least a 2 and a 1/2 to make it a little bit easier for me. And when I say fancy factoring, I'm looking for a GCF that I can pull out of this derivative. we really just technically have two terms here. So in that first and second term, looking at the numbers, they both at least have a 2 in common. So I can pull that on the outside. What else do they have in common? They both have this 25 minus x squared binomial. When we pull out a GCF, we always pull out the smallest exponent. The smallest exponent is technically this negative 1/2. So I'm going to pull that on the outside. And then we have all the leftover pieces. In that first term, I took out a 2. What's left over is an x, a negative, and another x. So that's going to become negative x squared. In that second term, we took out the 2, and then you have to kind of think about your properties of exponents. Right now, this is 25 minus x squared to the 1/2. I took out a negative 1/2. So in your head, you have to think negative 1/2 plus something gave me positive 1/2. Well, that's going to give us something to the first power. Tidbit of advice, since this came from the product rule, which came from the derivative, like that exponent is going to always end up being a 1, just because of the nature of the derivative. And then I can go ahead and simplify it from there. So what is a prime? I have 2. I have the square root of 25 minus x squared in the denominator. And then my numerator, this is going to become 25 minus 2x squared. Questions on that derivative? Yes, Matthew?
When you wrote the negative x squared, what happened to the other 2?
When I wrote this one,
No, the one off to the right. The negative x squared. I
I don't know what I'm looking at.
Negative x squared. No.
The
Oh,
bracket.
In the orange bracket.
in the orange bracket.
Negative x squared.
Right.
Oh, that one. I see it. I'm being dumb. Negative x squared plus negative x squared is negative x
I
squared.
meant like when you went to go simplify it. Oh, it's because of 2.
You got it? Okay, that was confused too. Okay, so we have our derivative. Again, we need to find minimums or maximums. So what do we need to do with that derivative? Set it equal to 0 and find when it's undefined. So that basically the numerator equals to 0 and the denominator equal to 0. Setting that numerator equal to 0, so that 2 is a coefficient, so I don't need to worry about it. That other factor, we're going to get x is equal to plus or minus the square root of 25 halves. Not the prettiest number, but that's what we get from the numerator. Looking at the denominator, this is where the derivative is undefined, where minimum and maximums could also occur. So 25 minus x squared equals 0, so x will be equal to plus or minus the square root of 5. Here's one where we have to do a little bit more work, because we did not just single critical point. We ended up getting 4 critical points. One of those critical points is going to give us the maximum area possible. Some of them, if you kind of use logic, you can probably eliminate them pretty easily. I'm going to do a candidates test just to kind of show you the calculus that we're doing. So I have my critical points, and I'm just going to put them in order. That's what I'm used to doing when we do a candidates test. And remember, when you make a candidates test, you always plug it into the original equation. So we want to find a maximum area. So I'm going to be plugging this into the area equation. You don't have to plug it in completely if you can kind of see where it's headed, because some of these you can eliminate pretty quickly. For example, if I plug in -5 into this equation, we'll have 2 times -5 times the square root. Well, 25 minus a -5 squared is going to give you what? 0. So that whole area would be 0. Well, is an area of 0 going to maximize area? No, like this is going to be 0. If my pen will write 0. So like we're not going to use that value because clearly 0 is not a maximum value. The same thing's going to happen down here if you plugged in +5. Like you would have 2 times 5 times the square root of 0. A value of 5 is not going to give you a maximum area. If you knew what this figure looked like, so if x was 5, that would be the p-value would basically be on the x-axis, and clearly there's no rectangle there at all. So that's why those were eliminated. And then between the other two, you can also probably figure out which one is easy to eliminate if you're maximizing the area. So in this first one, we have 2 times this negative root 25 over 2 times like a square root. Well, this product is going to be what type of number? Negative. Is a negative number going to maximize area? No. So which one's going to maximize area? It's going to be that positive one, which many people, you wouldn't have to do a candidates test if you're able to recognize that, like, I need that positive coordinate, and I don't want the one to be 5, because then I wouldn't really have a rectangle there. Could plug it in, I'm not, but it doesn't want me to answer the question. Which coordinate is going to maximize that area? Well, the one that maximizes the area is when x is the square root of 25 over 2. And then the y coordinate, I could just plug it into the equation. 25 minus 25 halves, since I'm squaring it, that would be the coordinate. Which coincidentally, if you simplified it, again, I don't really care about simplified answers, but it's the one where the x and the y coordinates are the same. Which do make sure you're careful, that's not a square, that's kind of like 2 squares sitting next to each other, will be the one that maximizes the area. So a lot more algebra in that one, but again, the idea is still the same. Primary equation, write it in terms of one variable, find its critical points, and then one of those critical points will be your answer. Last question. This kind of takes you back to the problem I was alluding to earlier. So we have an open top box, and it's going to be made with a single sheet of paper, and you're going to cut out the corners from that sheet of paper and basically fold up the flaps to create a box. You have a 24 by 24 sheet of paper, so it's a square. And just so we're consistent with our variables, I'm going to say that the square we're cutting out is like an x by x square. Try that one on your own for me. See if you can find the cutout you would need that would maximize the area, the volume, excuse me, of that box, using calculus to solve the problem. So,
I think you can just plus y equals
that's what that algebra. You can take the square root across plus or minus signs. I would put pound sign here. And again, you're maximizing volume, so you need to find a volume equation. You need to write it in terms of one variable. And then I would probably simplify that volume equation before you want to go take the derivative of it, unless you just want to do an extended product rule, which you don't. And then find the critical points, eliminate critical points that don't really make sense for that problem. Yes.
Secondary.
But I don't know the secondary thing. Like, that's the secondary equation, kind of, we already took care of it. Yeah, I knew that, I knew this. Like, it was already in one variable.
Yeah, I did that, bro. One ninety-four.
All right, so there is my work. Again, kind of following that same process. Optimization problems are pretty predictable. Like, you need one equation in a single variable. I need a volume equation, so I'm thinking about this box. If I let x be the size of a cutout, this is a 24 by 24 sheet of paper. If I'm taking off basically x from either side of it, so the base is a square, so each, I call it the length and the width, but it would be 24 minus the 2x. The height's going to be an x when you fold those flaps up, so that's what the height's going to be. Could do the extended product rule. I went ahead and FOILed that all together so I could just use the power rule. And then we want to find the critical point. So I went ahead and found the derivative. This is a polynomial, so it will never be undefined, but I can go ahead and set it equal to 0. Setting it equal to 0, we have critical points at 12 and 4. I made a Canvas test, but many of you could probably eliminate one of those pretty easily. Like if you go back to the original diagram, if you cut out a 12 by 12 box, like you just cut your paper into 4 sheets of paper, there'd be nothing else left to fold. So what is going to maximize that volume? The maximum volume for that is going to occur when X is 4. So we're basically doing a 4 by 4 cutout to give a box with a maximum volume. Questions or concerns about that problem? All right then, so for your homework, it is in the textbook shared with you in OneNote. So I assigned homework 3 on Monday. Today we're going to be looking at homework 4, optimization.